actually. Uh, yeah. Now, so we are looking at this, energy conservation, the lessons learned, and the road ahead. So, already a lot of things have been done in the field of energy efficiency. Hello? Yeah, is it okay?
Yes, sir. Yes,
Hello?
sir. Yes. Yes, sir.
Okay,
Yes,
right.
sir. Thank you.
So, now, of course, we have seen a lot of exploitation of the renewable energy. See, we have this non-renewable energy which is accounting for 90% of the world's energy requirement. Coal, oil, and gas alone is accounting for 90% of the global energy requirements. So, what is contributed by renewable? We have seen a lot of change that is taking place in the renewable energy market. Wind power has made a lot of penetration. So wind and we have solar, and wind and solar been the talking news over the last 10 years. We find that almost every industry or institution having a solar panel generating at least about 20 to 30 kilowatts of power. Wind also, a lot of inroads have been made in the field of wind, but in spite of all that, so much of efforts have been put in, but still the renewables themselves contribute only less than 10% of the total energy requirement. See, this is primarily because considering the kind of activities that we are performing with the oil, coal, and gas, you cannot totally replace this component by solar or wind. As you know, wind energy is produced maximum for about 20 to 25% in a year. The maximum wind speeds you have for generation. So the capacity factor, how much time it will generate power in comparison to the maximum power it can generate, that capacity factor is only 20 to 25% for a windmill. Similarly, for solar energy, we know that the solar window where the maximum light is available is somewhere about 4 to 5 hours. So that is all that you can have to exploit solar energy. So we find that though the installed capacity is huge, say 100 kilowatt solar if you have installed, ideally what you will get is maybe 400 units per day maximum. 400 to 500 units per day is what you get from 100 kilowatt solar power plant which is installed. The same thing, if you have a 100 kilowatt, say coal fired power plant, for example, you will get almost about 2,400 units. So you see the investment you're making for a coal fired power plant, investment making for your solar power plant, the capacity factor itself is quite significant in determining your economics, how much is the payback period, and all that. So as a result, you have invested a lot of money in the solar panel, but you're getting only about 400 units for the 100 kilowatt system, which means the payback period may be 6 years or 8 years, depending on how much energy is consumed or generated. So, of course, all this renewable energy is all supplementing some of the energy that we are using, but it cannot totally replace the kind of energy that we are using in terms of oil, coal, and gas. Yet another thing, in terms of thermodynamics, also, if you see, what matters is the temperature. It's not the energy. Energy, kilocalories or kilojoules, so many millions you can have. But ultimately, what can really do the work is your temperature. That's the second law of thermodynamics. Now, when you burn oil, you can go up to temperatures of 1500, 1600 very easily. But same thing with the solar energy, next to impossible. So just by focusing the solar radiation, you will not be able to reach 1500 so easily. So there are some limitations in the use of renewable energy. It cannot totally replace all the energy that we are using. So to a certain extent, it is supplementing. And we all know this that coal, oil, and gas, the fossil fuels as they are called, they all have limited resources. They're all going to be over in no time. Coal may last for about 100 years. Oil is also another precious fuel. It may last for about 40 years. And unfortunately, in India, we don't have much of oil deposits. We are importing a substantial portion of your, nearly 80% of your oil is imported. So the import bill itself runs to several lakh 10 lakh crores is the energy bill for the country every year. Natural gas is abundantly available and widely available, and the problem with gas is the transportation. So it's available in many parts of the world, but how to transport this gas? You have to lay long intercontinental pipelines, or you have to liquefy the gas and bring it. We are also doing that in India now. We are getting LNG, liquefied natural gas. We liquefy the gas, convert liquid, and bring it by ships. And we have ports being built, or many ports have already come into operation, like Dahej and Cochin. So we have ports which are in operation to handle liquefied natural gas. And that is also going to be over in about 60 years. That's the lifespan of gas. Oil will be over in 40 years. Coal will be over in 100 years. So this is the scenario. So that means we are fighting against a wall. There is a limited resource, and at the same time, all countries want to develop. So the energy consumption will go up. The energy consumption is increasing on one hand. On the other hand, the deposits are depleting. So it's a back to the wall situation where very soon we will be devoid of all these precious resources. Now, if you look at this graph, it's a very interesting graph. Who actually discovered this coal? Somewhere in 1756 in Pennsylvania, somebody was drilling the earth for water, and suddenly they found this slimy substance coming out. So in 1756, they found out this oil. Simultaneously, coal was discovered. So 1756 is somewhere here. But this coal oil, as you would see, that it has taken millions of years to form. When some big upheaval came, all these fossils got buried into the earth, and it took millions of years for all these fuels to form. 1756, the first oil was discovered in Pennsylvania in US. Simultaneously, coal was discovered, and then they found it can burn. So the controlled fire was discovered, and now you can see then they started making so many things with energy, the industrial revolution. So energy starts zooming up, and the peak is already over. Now we are in a depleting region where very soon it will all be over. So already 60% of all resources have been consumed and will not exist for future generations. So what the next generation will do is a big question mark. We were talking about the utilization of energy. So this one particular picture sums up the efficient use of energy. See, this is this red color. Can you see the mouse
No,
moving in
sir,
my screen?
sir, just I will interrupt you. We can't see your slides, sir. That first slide is as it is.
Oh, it's not moving.
No moving, sir.
Okay.
Please.
Right.
Now it's okay. Now it's okay.
Okay, I was on my, okay, sorry. I was
Yeah.
on my full screen. Okay. Now, this is what we discussed actually, renewable, non-renewable, solar energy cannot totally displace the fossil fuels. We still have to depend on fossil fuels. Then we saw this coal, which will be available for about 100 years. and oil will be available for about 40 years. Gas will be available for about 60 years. So this is the scenario. Okay, and now this is what we were discussing. Coal and other fossil fuels have taken hundreds of millions of years to form or are likely to deplete soon. And we already consumed 60% of all the resources and will not exist for future generations. So, okay, what we're talking about this, the what took millions of years to form, suddenly one day in 1756, the coal was discovered, and then the Industrial Revolution has consumed all the energy. 60% of all is over, only 40% is left. So, what the future generations will do is a big question mark. Now, this is the graph we are talking about. You look at the US economy, how the energy is being utilized. So 84% of all the energy is coming from fossil fuels, and 7% is through non-renewable nuclear, and then there's a little bit of hydel biomass. So all this contributes to the inputs. So these are the total energy inputs. How this energy is actually getting utilized? If you see, the useful energy is only 9%. So only 9% is the useful energy. And 7% is going for petrochemical, which is also can be considered useful. But the losses, if you see, 41% of the total energy used in the US economy is going as unavoidable energy loss, or unavoidable energy waste, we call it. What is unavoidable? When there is a waste, why it should be unavoidable? So this is a question we should ask. So as we know from thermodynamics, 100% energy conversion is not possible. When you look at a diesel engine, what is the efficiency of a diesel engine? Hardly about 30%. So that means about 30-35% goes in as heat loss through exhaust, another 35% as heat loss through coolant in the radiators. So this is a limit. The thermodynamics sets a limit on the conversion efficiency. The second law of thermodynamics says that 100% energy conversion is not possible. When you convert energy from one form to another, there has to be a loss of energy. This is inevitable. Same for a power plant also. If you take a thermal power plant, the efficiency is only about 30%. So 70% is lost in the thermal power plant itself. This is again because of the laws of thermodynamics. Whether it is in India or Japan or Germany, US, anywhere, the efficiency of a typical thermal power plant will be 30%. So this 41%, nothing much can be done. Some amount of energy loss according to the engineering thermodynamics, it will be there, so we cannot avoid it. Like we cannot say we will, in a vehicle for example, the exhaust is coming. We cannot say that we will close the exhaust and save energy. The vehicle will not move. So some heat rejection has to take place, some energy loss has to take place in order to get the work done out of the heat. Then we have 43% is unnecessary energy waste. So this 43%, what is unnecessary energy waste? Like for example, we discussed about the air conditioner. So you are setting the temperature at 22 degrees, it's a waste. And then you are putting a blanket and sleeping. Temperature is set at 22 degrees, 20 degrees, then you can see people using a blanket covering themselves. So it's a waste. When you are using an air conditioner, what is the optimum use of air conditioner? You should be able to sleep comfortably without a bed sheet or a blanket. Then that temperature is the optimum temperature. So anything below that is a waste. So these kind of wastages are the ones which we are focusing for energy conservation. This 43% can be saved. So if you look at the energy efficiency in the US economy, it is only 9%. That is, the energy input, useful output is 9, the remaining are the losses. So efficiency is output by input. Output is 9%, 9 input is this, so 9% is the efficiency. When you can recover this 43%, then the energy efficiency becomes 53%. If you see the typical losses in a power plant, how the electricity comes to our place, what are the various losses and how the efficiency can be assessed. An interesting slide. If you see that this is the thermal power plant, we are putting coal into the plant. Let's say 100 units of energy is going in the form of coal. 70 units is lost in the thermal power plant itself. Only 30% comes out as electric power. Now this power that is coming out, then it has to run through the wires, long distance, transmission and distribution loss. That's about 8 to 9%. Then it comes to your industry. Transformer will be there. Transformer is highly efficient, so we ignore it. 99% is the efficiency of a transformer. Then it comes to the motor. In the motor, there is 10% loss. Then the motor drives a pump. In between, there is a pulley or some coupling where there is 1 or 2% loss. In the pump itself, there is about 25% loss because the efficiency of a pump is 75%. And then you have, you see that water is usage is very high. We don't want so much of water. We want to reduce the water flow. So we throttle the outlet of the pump. In throttling, by closing the valve, you lose about 33%. Then the friction losses in the pipe is about 20%. So ultimately, what reaches the overhead tank is 9.5 units. So the efficiency, if you see, what is the energy in the overhead tank water? What is the energy input to the power plant? It is only 9.5%, 9.5 by 100. So this shows that and this is not the end. So finally, suppose you open a tap and don't close it, forgot to close it, then the entire 9.5 units is gone down the drain. So efficiency is further determined by how you are going to use this water, how efficiently you are going to use this water. When you save on the water usage, perhaps you can retain this. Otherwise, finally, what is the actual requirement of the water? How much energy is there? And into this, if you see, it will be 1%. So many of the equipment, what we use, whether it is a power plant or a simple compressor or a pump or any other equipment, the efficiencies are pretty low. So we are also looking at the adverse impacts of energy use. So many things are happening like global warming, acid rain, ozone layer, and also locally it affects. So all these things are something unnatural we are doing. Energy use itself is unnatural. Somewhere inside the earth we have dug up and then we are burning it and using it for so many other purposes. As a result, the environment is getting worse and worse. Now the substitute for fossil fuels, so many things have been explored, and ultimately we have this current day solar photovoltaic, the solar panels that we have for generating electricity. So as we have seen that many of these things can only supplement, it cannot replace. So also the windmills, and in between we had this fuel cell where directly without combustion you have the hydrogen based fuel cell where you need to get hydrogen So once you get hydrogen, the hydrogen will pass through a proton exchange membrane where protons will pass, electrons will not pass, so electrons will go through a circuit and create the energy. So this is one technology which was much talked about, and we also have fuel cell powered cars available. But how do you get hydrogen? So this is a big question mark. This hydrogen, actually what is used now is coming from natural gas. Natural gas is methane. So when you put some steam into the gas, it evolves hydrogen. That hydrogen is used for fuel cells. But in the long run, it may be difficult when natural gas runs out. What are the options available for getting hydrogen is very difficult. Electrolysis of water is very energy intensive. So the amount of energy that you are putting into electrolysis is much more than what you will get out of the hydrogen from the electrolysis process. So wind is already exploited to the hilt. So we have many parts of Gujarat, Maharashtra, Tamil Nadu, which have been the forerunners in this wind potential. So looking at the potential for energy conservation, um, the government has come out with this Energy Conservation Act, and this act is for providing efficient use of energy and its conservation and for matters connected thereof. So there are many aspects to this Energy Conservation Act. There are some mandatory things that needs to be carried out, like some of the industries have been given targets, energy saving targets, and they need to fulfill the targets, otherwise there will be a penalty, and it's a penalty and reward scheme. If you perform better, you get a reward. If you don't, then you end up with penalty. Then we have this star labeling scheme, which is also a part of the Energy Conservation Act. Many of the appliances have become star labeled. So the government on its part has brought out a law to make energy efficiency, to give a thrust to the energy conservation movement in India. So when we look at the various fuels available, basically the source of all energy that we use, whether it's electricity or heat, whatever it is, some fuel is burned somewhere, predominantly, barring say hydel and all that. Otherwise, the thermal based electric power generation also, if you see, the thermal based power station contribute to the maximum. So it is a source of heat which is used either for power or for the process, and there are variety of fuels being used, starting from petroleum fuels, coal, lignite. Lignite is a younger form of coal, and agrofuels. So a lot of agrofuels are also being used in the country. An agrofuel is something like rice husk, or bagasse is an agrofuel. Sugar cane, after taking out the juice, what is left is bagasse. It's an agrofuel. And now these are the petroleum fuels, different petroleum fuels available: LPG, naphtha, petrol, kerosene. But what we use in the industry is mostly the furnace oil. Furnace oil is the bottommost product of the refining column in the petroleum industry. So furnace oil has got 10,500 kilocalories. Then we have another fuel called LSHS, basically low sulfur fuel. Furnace oil will have about 4% sulfur. Sulfur is quite detrimental to the operations as well as to the environment. So we have a crude which is low in sulfur. From that, if you get this bottom product, it's called low sulfur heavy stock. Then we have light diesel oil. These are all some of the fuels, petroleum fuels used in the industry. And these are the different types of coal. You have oldest coal, high calorific value coal is anthracite coal. This is bituminous, subbituminous. Lignite is the youngest coal. If you allowed that to remain inside the earth for another millions of years, it would have become anthracite coal. But before that, we have dug up and we have taken the lignite out. And these are the agro fuels. Rice husk is a very good fuel, having 3000 kilocalories. Many of the boilers, if you go to Chhattisgarh or any of the Indian states, rice husk, you will find that is used in the loose form like this or as a briquette. It will be converted into a briquette in the form of cakes. So then it can be fired in a boiler. So these are, in fact, this is a pellet actually. This is a very thinner form of a briquette. So from rices, they extrude this rices by putting some binder and into a die, they'll extrude it. So you get pellets like this. Then we have firewood, the conventional age-old fuel firewood, and bagasse from the sugar plant is a very common fuel, agro fuel. In a typical, when you start the energy saving activity, we need to understand how the heat is produced. Right from the moment how to extract the maximum calorific value. A fuel can, what is the calorific value? What is the amount of heat that a fuel can give? 1 kg of fuel can give, that is calorific value. Now, in this, these are all the components. You have carbon, hydrogen, sulfur. So all these contributes to the calorific value. Okay. So we have hydrogen also. So basically all fuels are hydrocarbons. They have carbon as well as hydrogen and little amount of sulfur. So carbon, when it burns this much of kilocalorie, it gives. Hydrogen gives enormous 29,000 kilocalories of hydrogen per kg of hydrogen. Now this is released. From here starts your energy efficiency exercise. Now we have a fuel which is having so much of calorific value. Where every kilocalorie is going, that we need to account. So once we can account that, then you can find out what is the useful energy, where are the losses taking place, and how to minimize the losses. So basically that's how they say it's an auditing. Auditing means what is the total income, where all the expenditures are taking place, and we try to plug the unnecessary expenditure. So this is exactly similar to that. Total kilocalories released by the fuel, where all it is going. What is the useful kilocalorie? What are unnecessary kilocalories going in the form of losses? And how to minimize that. So this is the first fundamental step, understanding the evolution of heat from the fuel. And in the generation of this, once you burn this fuel on combustion, what are the factors which are going to influence combustion? So that needs to be looked into. One is, of course, how much air we are going to give for combustion. Too much of air means too much of heat loss. Too less air means unburns. So in between, via media, there has to be a good combustion point where optimum air is provided to ensure complete combustion. Then the losses will be minimum. So we focus on this. And then you also look into the unburns. So when you do an audit of the boiler, for example, typically what we do is we take a boiler and then what is the fuel fired, what is the total input, so kilocalories, and what is the total output from steam, what is the total heat in steam. Heat in steam divided by heat in fuel gives the efficiency of the boiler. So let us say 80%. Where is the 20% going? So it is going through the stack, something is going through the radiation convection, and something unburnt, like in the coal-fired boilers, you have unburnt coal falling into the ash, along with the ash. So these are all points of inefficiency. Now, when you say 20% is exhaust, why 20%? Suppose when you reduce the air little by little, it can come to maybe 16%. How to optimize the air? So all this means we are contributing towards improved efficiency. So we want target efficiency is 83% or 84%. Measured efficiency is 80%. So where exactly we are losing? Is it because of using too much of air, which is carried out as exhaust, or because of this unburns and fuel? So that means we need to do a detailed exercise on the efficiency, where all the 20% is going, why 20% is happening, what are the reasons. So once you attack that, your efficiency can be improved. So this is the approach. So these are all the different boilers, as we said earlier. This is a typical oil-fired boiler, a coal-fired boiler. Earlier days, the chain grate. The coal will come through a hopper and fall. Slowly, it will come here and burn fully, and ash will come here. And this is a suspension, a sprinkler stoker, spreader stoker. So there's an impeller. Coal as it comes, it is thrown to the other side. So the chain will be rotating this side, and because of some turbulence, the efficiency is higher. Now we have this fluidized bed boiler, where you can see this whole thing, coal particles on the bed, and you have air coming from the bottom, which is pushing the coal up. So coal is jumping and burning in suspension. So this is the evolution of the technology side. And what are the most important things is also the instrumentation part. Like for example, when you want to know how much air is going to be there, excess air, for combustion, how much air is used, you need some kind of a measurement. So the excess air that is coming out, that is given to the fuel, is measured by this oxygen analyzer. Today, as we talk about developments in technology for efficiency, we need to talk about developments in the instrumentation side. A lot of portable instruments have come. This is an oxygen analyzer. We have, of course, portable kit. This is an online oxygen analyzer. Because the operator needs to know, when he wants to maintain the efficiency, the operator who is operating the boiler needs to know how we can do that, how we can maintain high efficiency. He should know that using too much of air means wastage is too much, so we need to control. How does he know whether it is too much of air or less of air? So he needs some kind of an input. That input comes from this oxygen analyzer. So if you put it in this chimney, this will indicate the oxygen in the exhaust. The oxygen in the exhaust is an indirect indicator of the air you are using for combustion. So these are also important in an energy efficiency exercise. Instrumentation can reveal a lot of things which are otherwise hidden. The boiler has generated steam, and steam is going to be used in the power process, and we need to understand the fundamentals of steam. How steam, why steam, and how much steam, all these questions come into play. As we know that when steam is generated, you have a portion of sensible heat here, latent heat here. So it's the latent heat which is actually going to give the heat. So latent heat is reducing with increasing pressure. As the pressure increases, latent heat reduces. So our objective always should be to use the steam at the lowest possible pressure, so that the full latent heat of steam is utilized. And at what pressure you're going to use, what temperature is required, all this will be determined by the properties of steam. Then of course the steam circuit here. In a steam circuit, you have steam going into the equipment. So you have a steam going into some equipment, and then there is something called a steam trap. You'll be learning more about this in the next few days. The steam trap is a device which will not allow steam but allow only the condensate. So we want the steam to condense and give up the latent heat. And steam trap is a very important equipment device in the steam distribution system. Now, if the steam trap is not working properly, then there will be a lot of losses in the steam system. So, the monitoring of steam traps is one of the measures for improving the steam system efficiency. The steam, just we saw that for power plant, it was only 9.5% end use efficiency. Similarly, for the steam also, you will find that, once a boiler is generated, 100% we are putting into the boiler, and efficiency of the boiler is 80%. That means steam, what is coming into the boiler, carries 80% of the input heat. 20% is lost in the boiler itself. Now, as the steam goes through the main pipelines, there is a 5% loss because of the radiation and convection. In spite of the fact that you insulated, still there will be some loss. So 75% goes in the process. In the 75%, actually the product itself carries only 35% of the heat. Remaining 25% is lost. And the steam condenses, 15% of it is returned back to the boiler as condensate through the condensate return system. Now, where do you focus on reduction? See, the boiler itself, as we have seen, technologies have emerged to an extent where the efficiency of the boiler is 80%. Then the 20% what further we can reduce. So it becomes a challenge. Steam mains, already insulation has been done, there's a 5% loss. So there also, further you cannot insulate. Maybe it will be too expensive to insulate, not economically viable. So 5% let it remain. Now 75% is going into the process. So this is where a major portion of the energy saving lies. Here if you save maybe 1%, at the input of the boiler you may be saving about 5%. And there is a lot of scope for saving energy in this process. So the focus should shift. Earlier, we have been focusing only on the boiler, only on what is the excess air, what is the oxygen percentage, how we can reduce unburns. Maybe a little bit, 1 or 2% you may gain, but it comes through a lot of hard work. But whereas in the process, how steam is used in the process, why steam should be used in the process, what is the temperature required, what is the pressure required, how much steam is required. So you make a theoretical heat and mass balance to find out how much steam is actually required and how much steam is actually used. So you know what is the difference, where the loss is taking place, can we reduce that loss. So like this, you need to attack the end use, where finally the energy is being used. That is the point where maximum energy efficiency lies. So if you see the generation efficiency, the boiler itself it is 80%. Then distribution from boiler to the final process where the steam is delivered, in between the pipelines, is about 83% efficient. That means that 5% loss if you take. Utilization efficiency is only 47%. That means this is the place where maximum potential lies for energy savings. So you need to focus on that. And if you see like overall efficiency from the fuel's heat to the requirement, what is the efficiency? This into this into this. So it's only 35%. So it shows that there is a huge potential for reducing the fuel consumption not by focusing on the boiler, but by focusing on the end use in the production process. So, for example, this is a typical one of the case studies where they were using some heat in the form of, let's say, steam for some application. Some heating was required for an application, steam was being used, and here what was done is an integration. So, an air compressor, the efficiency of an air compressor is only 10%. Almost 80% of the input energy to the compressor goes as heat. So we should know this. Now once we know this, there is a heat available from the compressor. There is a heat requirement in the dryer. How to integrate? So that means you can put a heat exchanger in the air compressor and take that hot water and use it for drying energy requirement. So this is a simple way of integrating. So there is no need to focus. In this case, the focus is not on the boiler, it's on the production. There is a requirement for heat in the dryer. There is a heat available in the air compressor. Today, nowadays, the various compressor manufacturers themselves have come out with this system. So they ask you whether you want a heat recovery. If you want, they'll give you a heat recovery device, a plate heat exchanger, from which you will get about 90-degree hot water. This 90-degree hot water can be used for any of the heating applications. And so there is another case where, earlier they were using a briquette fired boiler, just sawdust briquettes. Sawdust briquettes are used as fuels. If you use a bigger size briquette, unburns are more, were found to be more. So what we did was slice these briquettes. So during the purchase itself, we asked the person to slice this into a maximum 2 inches width. Instead of having a 6-inch or 8-inch, we asked them to make it 2-inch. So as a result, the combustion improved and the unburned losses reduced. So this is a typical example how the size is important when it comes to complete combustion. The lower the size, particle size, the better is the combustion. And here also there is one hot water generator. This is similar to a boiler. So in some cases we find that still there is this lack of basic heat recovery system. So the temperature here, what is going out is 375 degrees, and we put a heat exchanger to recover. Heat recovery is one area where still a lot of potential lies. So in this hot water generator, this is this 275 degrees centigrade hot air, flue gases. So instead of going to the chimney unutilized, we put a heat exchanger and recover the heat. Yeah, this is the picture of the compressed air. You can see this compressed air. These are the outlet ducts from the compressor, outlet ducts. 90-degree hot air is coming. So the dryer is in this room, what you see here. So you need to only connect this ducts to the dryer here, open the wall a little bit, have a common duct for all these 4 compressors are there, and take it to the dryer. So by doing that, the savings for this company was about 4.8 lakhs by using the heat of compressor for drying applications instead of steam. Now, the yet another important thing, what as energy auditors you need to further do is to understand the process. Many times we only go after the energy. So if there is energy used in the boiler, you only restrict yourself to the fuel and fuel and steam generation. So most of the attention is towards the boiler. If it's an electrical energy audit, most of the attention is on the motor. So we measure what are the motor horsepower and voltage, kilowatt, current, harmonic, so many things we measure. But more importantly, what is important is to understand the process. What is happening in the process? Why at all energy is required? We have to start from that. Why at all energy is used in the process? And when you start like that, then it throws up so many questions. Like here, this is a typical chemical plant which is manufacturing penicillin G, a bulk drug manufacturer. So this is a flow chart. So these are all the various process steps, and now the energy usage is given here. Okay, so the steam distribution is also shown here. So we start the audit by tracing the steam, where all steam is going, and wherever possible try to quantify the steam for different processes. We may not have meters, so the challenge is without meters how we can arrive at a typical balance, steam balance. So we have to go through the basic energy balance route, make a heat balance and find out what will be the requirement here, what will be the requirement here. So at every stage you can find out using this heat balance method, or you can even collect the condensate. When it's a low pressure steam, what is the condensate coming out of each equipment? That is going to be the steam required. So you make a tentative steam balance. Some data is better than no data. Then you see what is steam consumption, just a specific steam consumption per ton of product, how the steam is varying over the months. You ask why, how there is a variation. So again, these are all the data analytics which throws in a lot of light about your energy use pattern. And there's a boiler itself. So make a flow chart of the boiler, see what is happening in different areas. Fuel is supplied, air is supplied, and then this is the flue gas path. So you need to have a bird's eye view of the whole boiler system, for example here. So on analysis we find that as you walk through, there is a place where some water was flowing, and when you try to probe that, we find that the deaerator water is overflowing. Overflow water is going into a drain because of some changes in the level setting. So that level setting was 40%, which led to overflows. And nobody knows because it is going into an underground closed drain. The pipe is taken and put into an underground drain because so it should not flash, but then nobody can observe that. So on an audit, you find that this is a simple wastage which is happening. By changing the overflow setting from 40 to 20, say about 7 lakhs. Right, and then this is the blowdown system. You see whether there is a potential for heat recovery. Can we have a flash tank and generate flash steam? Can we have a heat exchanger to recover the blowdown? So we are only focusing on the wastages, various wastages, and how it can be minimized or eliminated. Then we look at the other detailed processes in the system, the extraction process itself. In one of the processes, so here we are trying to identify where exactly the heating is required and how much steam is used. All this are being identified here. Okay, So in this is a case for solvent recovery where this butyl acetate is a kind of solvent which comes here, and it has to be regenerated. It has to be made as a pure solvent. It is absorbed. Solvent has absorbed the penicillin G and it has to be regenerated. So it goes through an evaporator where we use steam to heat it, and then it is condensed. So this is a heating cycle, and finally the butyl acetate has to be cooled. It has to be cooled about 40 degrees centigrade. Only then it is a safe storage. This is the system. Now in this system, the heat recovery, if you see the potential, is a very simple energy saving measure in the process. This is a butanol which is coming at 30 degrees. We are using steam to heat it to 124 degrees centigrade and again cooling it and storing at 40 degrees. So here we are using 130 kg per hour of steam and 37 kilowatt cooling water pump to cool it. Now if you carefully look at this butanol is coming. We are heating and then 124 degrees it reaches. Again we are cooling it to 40 degrees. Now what we are going to do is, see, this cooling will now be done by this impure butanol. This we will take this here and use this cold butanol 30 degrees to cool this hot butanol. So this 30-degree butanol will go here. It will reach one temperature and then you go into the evaporator column. So instead of using steam and cooling water, we use the cold butanol to cool the hot butanol. At the same time, this is getting preheated. So if you see, in this case, see the impure butanol 30 degrees, it goes into a preheater 80 degrees. The preheater is actually the hot butanol here 124 degrees. That is what is going to heat up this impure butanol. So 124 degrees now becomes 40 degrees with minimum use of cooling water. This cooling water requirement reduces dramatically, and steam consumption also reduces dramatically because after 80 degrees only it is going to the evaporator. So you can see here from 130 degrees steam it has come down to 75 kg per hour. So dramatic reduction in steam consumption, which saves them about 3.6. So these are the measures which we are targeting, and these are the this is the approach we should take, where final end use, where is the energy used, and what are the options for minimizing the energy use. A huge potential still lies here. It's a gold mine that is waiting to be tapped, and I think at the end of the program you will pick up this kind of measures to apply in energy audits, these kind of measures. Okay. Yeah. So now this is what I just wanted to inform you about. Different ways of looking at things. The process-oriented energy audits, where there is still a huge potential available. Okay, so with this I end my presentation, and I leave the forum for any questions.
Yes.
Sir, in one of the sugar factory, they
Yeah.
have bypassed the deaerator.
Okay. Hmm.
So, what would happen to that system actually?
See, that means we first need to understand what is the function of a deaerator.
Correct.
So the deaerator is to remove the dissolved gases from
Correct.
the feed water. So all the oxygen and carbon dioxide, if any, has to be evolved, so that carbonic acid corrosion does not take place, oxygen pitting does not take place. This will be detrimental to the boiler tubes. So deaerator is a must. It is required unless chemically you are scavenging these gases. If there is a chemical treatment, it's so good
Okay.
that these gases will anyway evolve or it will not cause harm to the boiler tubes, then it's okay. But otherwise, deaeration, it's a thermal deaeration where you pass steam, you heat the water to more than 105 degrees centigrade so that all the dissolved gases evolves and comes out so that you don't have problems with the boiler tube failures at a later date. So avoiding deaerator is actually infringing on the functional requirement of a boiler.
True. Yes. True.
So anything which affects the process, it is not going to be energy conservation. Okay, so because now you may save a little bit of steam on the deaerator, but 1 year down the line, if a boiler tube punctures, it's a huge loss. So we should not tamper with the functional aspects of a system. Without tampering the functional, what is that we can do? In the deaerator itself, can we use some flash steam when the blowdown, any other waste steam is available? So these things have to be considered.
Sir, in some of the industries, the steam that is condensate is available around 40, 50 degrees Celsius max actually after completion of this, going through this all the processes, and there is no any need of the heat at that particular temperature. So how that heat content can be conserved, utilized for some application? For example, paper and pulp industry, we observed that
Hmm.
after completion of this process, that condensate is available, and there they don't need anywhere even for the makeup water also for as a condensate to the boiler. And still we
Mm-hmm.
got how to conserve that thermal content available in that steam. It is around 50 max 45 50 degrees Celsius. And even if you want to use that heat exchanger, again there would be some losses. So what
Yeah.
to do for such applications, low grade applications?
See, one thing is if it's not sufficient if you have a source of heat. There has to be a sink.
Okay.
Unless there is sink, you cannot use the source. That is number one. So whenever you talk about heat recovery, some uses should be there. If there is no use, then no point in recovering that heat. The second thing is, if you look deeply into the process,
Okay.
perhaps there are some areas still where this condensate water, like for example, if you're a mixing tank, so in a pulping section, they may be using cold water, DM water, and then finally using steam for heating the pulp. So instead, can you use this condensate water, hot water for pulping? Definitely, if you use it, that means in tandem, along with the energy study, you also need to take care of the water. So that means you also need to do a water balance. So do a water balance. Where is the total water quantity coming from? How much, where all it is going? And is there anywhere where this water is going to be heated? Definitely there is many places where hot water is being made. Hot water in the sense that cold water is being mixed and then you pass steam over it to heat the solutions. So in such areas, this hot water can still be utilized.
Even similar thing happens in the textile sizing units, sir.
Hmm.
Even whenever they are sizing with some chemical, they are adding some chemicals, they are mixing with the steam itself, actually hot water, and that
Yeah.
effluent, it is around again 50 60 degrees Celsius.
Hmm.
That's also
Yeah,
clear because it is being mixed with the chemical. It is being mixed with
uh,
the chemical. So we can't directly use that hot water or repellent. And if you want to exchange that heat again, the delta T that matters. Again, it will come to the 40, 50, 50 maximum 45 degrees Celsius.
yeah. Sometimes it may not be economically viable. It is better to
Correct,
waste some heat rather than trying to fully utilize all that waste heat. Because
correct.
economics will not permit. We can put a plate heat exchanger and get maybe 40-degree water.
Okay,
Even with a 50-degree stream, if you have 50-degree stream, we can get to 40, 45-degree water also with a plate heat exchanger. But we only
yeah,
need to, because many of these textile people, they use firewood as a fuel, low cost fuel,
true,
which
sir.
may not
True.
be. Suppose they're using coal or oil, then it becomes economical. You can put that and it recover. Even 1 degree saving is quite substantial.
Okay,
So we have to look at the cost economic, but technology is available. A good plate heat exchanger can recover the heat. You can make 40, 45-degree water, which can be further again recycled back into the process.
okay. Any questions from participants? Otherwise, even we'll request them to put on the chat box and we'll share
Yeah,
through the
sure.
emails. That would better you can
Definitely,
respond
definitely.
to that
Yeah,
question.
yeah.
So that we can continue with the second session.
Correct. Yeah. You can ask
That
them to ask any questions and you can mail me the questions.
so that you can respond and then again I will share with them. Okay. Yes.
Yeah.
Yes. Sir. Thank you. Thanks a lot, sir.
Okay, thank you very much for the nice meeting here.
Just the one
Have a
question.
nice.
I think one question is there.
Mhm.
That question is like, sir, when a new energy saving solution is recommended, how can
Mhm.
we relate? How can we relate new investment and energy cost reduction? How industry people will be convinced? It is from the
Very simple. See, whenever there is an investment required, we always need to look at the not the investment per se, but also on the payback period, simple payback period. So, in how many months or mostly it will be months. How many months it will pay back. So that is number one. But the biggest problem is the finance. The finance person is not going to accept. See, when there is always a competition, no, there is some new project development and energy saving investment. Which one the companies will prefer? Expansion or new product development, they will try to pump money. So this energy saving investment always will take a back seat. Now, in such cases, that is why this concept of systems of where energy management system, we have this ISO standard for energy management system, ISO 50001, in which the entire company is involved and commitments are made. So even the finance man has a role to play in that energy management system. So whenever there is a need, so you put up this financial proposal, the finance man knows what is the importance of it and getting things, probability of things getting granted is high when in such a culture of systems approach.
okay, sir. Thank you. Thanks.
Yeah, thank you very much. Thank you very much.